Hello everybody, and welcome to today's Chem lesson. Today we're going to talk a little bit more about electrons and their places in the atom. We're going to talk a little bit about Bohr's model and the shells that accompany it. We talked in our previous video about how electrons get placed in the shells, how many fit in the shells, and how we fill from closest to the nucleus outward. But something we skipped over a little bit was how Bohr even got to the point where he said that electrons live in these shells. Now, Bohr's experiment itself was a pretty complicated experiment. If we want to make a quick summary or analogy for it, that makes it a little bit more understandable, Niels Bohr took a ball, and he said, I am going to take this ball and throw it into the air. I'm going to start with my weakest throw possible, 0.1% of my strength. I'm going to throw the ball up with 0.1% of my strength and see how long it takes to come back down. And I'm going to increase, and I'm going to get stronger and stronger and stronger until I reach 100% of my power. And for each of these, I'm going to take the ball, I'm going to throw it up, and I'm going to time it and see how long it takes for the ball to come back. And now if you stop to think about that, you would imagine that 0.1% is the fastest to return back to your hand. Right? You throw it up, it comes back down, you catch it. And 100% would take the longest. You throw it up with all of your strength and it goes up, 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 and then it comes back down and you catch it. And that's what Bohr thought too, right? Everywhere, right, if we're looking at time and strength, the lower strength should be the fastest time. And the harder you throw it, the more time it should take. Right, 100% strength should take the longest time. Instead of this relationship, though, Bohr found that the graph looked different. He found that the graph kind of did this, where it immediately spiked from one amount of time to the next. So throwing the ball with 10% of your strength took the same amount of time for that ball to return than throwing it with 15% of your strength. And then 16% somehow jumped up a large amount of time. And Bohr looked at these results and he said, that's ridiculous. This doesn't make any sense. And what he came out of this experiment with was this idea of shells. Right? The electrons aren't just wherever. The electrons have these specific points where they happen to live. This solidified his version of the model, right, showing these shells and the different energy levels of those shells. And so what he said that electrons can be excited and given energy, which makes them jump up to a higher shell. And when they lose that energy and come back down, they return to where they started. The problem we have with that is that we give the atom energy for this to happen, right? We feed energy into the atom. But where does that energy go? Right? We feed the energy in. How does that energy come out? Right? Energy can't be created, it can't be destroyed. So if I give something energy, it has to release that energy somehow. And that release of energy is actually something you've seen a billion times before. That release of energy is falling from the excited state back to the ground state. That's how fireworks work. It's how neon lights work. It's how some fluorescent lights work. And we're going to walk it through, right? We're going to say we have something like lithium. And lithium has 3 protons, which means that a normal atom of lithium should have 3 electrons, which would be 2 in the first shell and 1 in the second shell. This is the default, the starting point. This is the ground state. Right, the ground state is the electron configuration that comes directly off the periodic table. The base, the starting point. Now, what happens when this atom absorbs energy? If we give this atom energy, if we take lithium and we put it into a fire, if we take lithium and we run an electrical current through it, adding energy makes the atom absorb some of that energy, and it causes an electron to jump. So instead of 2 and 1, that electron actually jumped to a higher shell. This is an excited state. Right? The electron has jumped up and is 1 place higher than it was before. It's out of place. Right? The excited state has 1 electron out of place. 1 electron higher than it should be. And this is a temporary thing. This lasts only a fraction of a second. And then the electron falls back down. The electron returns to where it started. But again, we want to think about, we absorbed energy, which made the electron jump. When the electron falls, we should release energy. And we do. When the electron returns back to the ground state, we release energy in the form of light. That's the neon sign. That's the firework. That energy that gets released is transformed from whatever it was to start, electricity or heat, and becomes light. And so as we return back to the ground state, as we complete our little cycle here, we release the energy we absorbed as light. Our electron jumped and then fell back down. Right? We return back to where we started. We've gone full circle. The really interesting thing, or the second, because this is already super interesting, the follow-up interesting discovery that was made was about the light that gets released. And what scientists discovered after studying different elements and the lights that they released, the colors that they released, they discovered that the light that each atom gives off is unique for that element. It becomes a fingerprint for the element, allowing you to identify an element based on the light that gets released. It's the same thing that lets you look at a firework, and if that firework glows red, you can say, that is potassium. And if that firework goes green, you can say, that is copper. Right? Those colors are so distinct and so recognizable that we can use them to go back and say, well, this element makes this color. And so we took all of those elements, we looked at all of the light they produced, and we found this idea of the emission spectrum, where we're going to focus here. Depending on what transition happens, depending on where the electron starts and falls down to, gives you slightly different wavelengths of light, slightly different energy. And the combination of these energies, right, looking at the different colors that get produced, we can mark this down as the fingerprint for an element. This pattern belongs to hydrogen. A different pattern means a different element. And so charting all of the different colors that get released when we look at an element under a flame or under electricity gives us this unique set of lines which we can then backtrack and say, okay, this set of 4 lines represents hydrogen. This set of 5 or 6 or 2 lines represents oxygen. And what this allows us to do is look at 4 different elements and compare it to a mixture. And say, well, if I know the lines for A, B, C, and D, and I look at the mixture, I should be able to identify if A or B or C or D is in my mixture. Let's take a really simple example. Right, these are the emission spectrum for atom A, element B, element C, element D. If I look at a mixture that has these lines, what 2 elements are in my mixture? Right? If you said A and C, you are correct here. Right? The lines from element A show up in my mixture. The lines from element C show up in my mixture. The lines from B, those ain't there. The lines from D, they're not there either. So this mixture would be some combination of A and C. Right? It can get a little bit trickier, right? What if we have, sorry, what do we got here? 1, 2, 3, 4, 5, 6. Right now, for this one, which elements are in my mixture? right? So it gets a little bit more complicated when there's more lines and some of those lines overlap. So let's take a closer look at this. If I want to claim that an element is in the mixture, all of the lines need to be there. So let's start with A and A's first two lines. These first two lines of A do not show up in the mixture. So A is not part of it. All right, this line is not there. Actually, I'm going to change color for this. This set of lines is not in my mixture. So A is not in my mixture, even though some of those lines are. It's all or nothing. So because A does not have some of these lines showing up in the mixture, A is not part of the mixture. B has all of its lines show up. So B is part of the mixture. C has all of its lines show up. So C is in the mixture. D has all of its lines show up. D is in the mixture. What happens to the mixture if I take away that line? What element is now no longer a part of the mixture? By removing the line that was here. So by taking out this one line, now I do not have all of C present. So C is now not a part of the mixture. It needs all of the lines, or it's not in the mixture, right? B still has these two lines show up. This line shows up. These two lines show up. So B is still there. D hasn't changed, right? All of these 4 and this set of 2 are both there. But by removing this one line, I've now invalidated C as a choice. And this practice, right, this method of saying, this is element D and B, really helped scientists fill in the periodic table. Because learning this new method allowed them to look at different things that they thought were elements, but turned out to be compounds or turned out to be mixtures, and allowed them to separate what they had labeled as one element into actually 2 different elements, and find missing pieces of the table. And to wrap us up for today, I actually just have one multiple choice question to kind of tie it all together. Which electron configuration represents an atom in an excited state? So here, what we're looking for the excited state is 1 electron out of place. 1 electron higher than it should be. So if we know that 2 electrons fit in the first shell, 8 fit in the second, 18, and then 34 as our maximum electrons, 282, everything is as close to the nucleus as it can be. So that's not our answer, right? Everything's already packed. 281, same thing. Everything is already as close to the nucleus as it can be. 28, same thing. Everything is as close to the nucleus as it can be. But 271, we have one electron higher than it should be. This could be 28. Right? And this would be the ground state of that element. But this is the excited state. Right? One electron out of place is all you need to be in the excited state. And with that, I'm going to wrap us up and transition us over to our Google Meet for attendance and announcements, and I will see you there.